This screencast is about the ionic product of water, which is the constant that we call Kw. So we need to consider what is occurring in any sample of pure water. Say if we have 2 molecules of water or 2 moles of water, then within the water sample you will have a certain amount of dissociation. It's not lots, in fact it's a really, really tiny amount. But we know that water can sometimes act as an acid and sometimes act as a base, and essentially that's what's happening between pairs of molecules in this. So we end up with our H3O plus ions, our hydronium ions, and OH minus ions in equal concentrations. We do usually simplify this to just being H2O, the equilibrium being with H plus and OH minus. So if we were going to write a Kc expression for this, then we would end up with the Kc expression I've written there, with concentration of H plus, concentration of OH minus on the top line, and then underneath the concentration of H2O. So essentially though here, because the dissociation is so small, that means that we end up with a really large excess of water. And that's the undissociated water. So that means effectively that the concentration of H2O is so large, we would consider it to be constant. So because of that, what we can do now is to write a new constant. So we incorporate our concentration of water into a new constant. So we're going to take it off that bottom line there, and we're going to combine it together with the Kc, these two things, and we're going to end up with a new constant which we're going to call Kw, and that is equal to the concentration of H plus times the concentration of OH minus, and that would mean that the units of Kw are moles squared dm to the minus 6. So how is the ionic product of water relevant to the pH scale that we normally work with? So we're going to be talking about the pH scale at 25 degrees C. You'll find out more about that later. The value of the Kw constant at 25 degrees C is 1 times 10 to the minus 14 moles squared dm to the minus 6. Of all the values in this, this is the only one that you'd actually have to learn. So do try and commit that number to memory. It's not particularly difficult to remember, but we do have to learn that one. So we're going to set up our mathematical expression. We're going to have our concentration of H plus times our concentration of OH minus, and we know that that is equal to 1 times 10 to the minus 14. So we know that the concentration of H plus is equal to the concentration of OH minus in here. So we can make our expression that the concentration of H plus squared is equal to 1 times 10 to the minus 14. So if we want to work out the concentration of H plus from this, then that will be 1 times 10 to the minus 7. And then we're going to do the pH of that. And remember, pH equals minus log to the base 10 of the concentration of hydrogen ions. So that will end up with a pH of 7. So that's the value that you've known pretty much all of your way through school. So what use is Kw? What do we really use it for? What we really use it for is for calculating the pH of solutions of strong base. When I was your age and I was doing my exams, I had this written on the front of my folder because I could never remember it. So if we want to work out the pH of a solution of strong base, then we're always going to use Kw to do that. So here's an example question. It's very simple. Calculate the pH of a 0.04 mole per decimeter cubed solution of sodium hydroxide at 25 degrees C. First thing I'm going to warn you again is to check what base it is. So we know that sodium hydroxide is NaOH, so the amount of OH minus ions we would get exactly the same moles as we would do for the concentration. Remember to watch out for things like calcium hydroxide, where you would have to double the concentration of the actual base itself in order to get the concentration of the OH minus ion. So just watch out for that, because the exam board can be pretty sneaky with things like that. So let's set up our expression. It's at 25 degrees C. I've reminded you at the top of what the value for that is. So 1 times 10 to the minus 14 is equal to the concentration of H plus, that's the thing we don't know, times the concentration of OH minus, which is 0.04. So the concentration of H plus is equal to 1 times 10 to the minus 14 over 0.04. So let me just stick that in my calculator, which gives me 2.5 times 10 to the minus 13. And then I'm just going to calculate the pH of that. So I'm going to do minus log to the base 10. And that gives me an answer of 12.60. Remember, we do tend to quote these to 2 decimal places. But again, check the question as to what it's asking for. And then also do a bit of a mental check yourself in terms of how sensible is that number that came out. So 12.60, that is a basic alkaline pH, so we know that it's probably going to be okay. If you get a number like 6 or something, then you know you've done something very wrong. Let's now consider the effect of temperature on our ionic product of water, constant Kw. So I've put in the table there already the values of the constant Kw at different temperatures, and you can see that the value goes up as the temperature increases. So I want you to consider that in terms of the equilibrium that we've set up. So essentially what we're saying is that as temperature increases, then the extent of dissociation also increases. So what must that mean about the forward reaction here? So we are increasing the temperature and we are getting an equilibrium that moves right. So it's shifting to the right and it's favouring those products, the H plus and the OH minus. So that must mean that this dissociation process is endothermic in the forward direction. Okay, let's think about this in terms of the pH. So we already know that if we have our usual ionic product of water at what we would consider room temperature to be, then that means that we get a pH of 7 at 25 degrees C for pure water. We increase it to 30 degrees C, then we end up, if we just plug these numbers in, you could do that, but I'll do it for you. We end up with 6.92 as the pH. Now, let's just consider what that actually means. So 6.92, if I asked you before we'd started studying this topic what you would classify a solution that had a pH of 6.92 as, you would have told me that that is acidic. However, what you need to understand from this topic now is that the pH range that you've learned all the way through school is only valid at 25 degrees C. So at any other temperature, the neutral point will have a different number. And that is because we have got a situation where the concentration of H plus is equal to the concentration of OH minus, because that's as it has originally come from this equilibrium over here. So we must have the same amount of H pluses as OH minuses because they've been dissociated from the same water molecule. So the concentration of H plus must be the same as the concentration of OH minus. So you only get acidity if you have got an excess of H plus ions. So we have no excess of H plus ions. So the water is not acidic. The pH scale changes at different temperatures. So at 30 degrees C, neutral equals 6.92. However, if you do get asked this question as an exam question, you can actually just write what I've put there, which is H plus is equal to concentration of H plus is equal to concentration of OH minus. That'll get you all the marks. It's the simplest way of writing that. So just for completeness, we'll just put the other values in for the pH at different temperatures. So if it's 40 degrees C, it's 6.77. And if it's 50 degrees C, it ends up as 6.63. Now it's time for you to check how well you've understood what we've been through during this screencast. So there are 3 questions here for you to have a go at. The first one is to do some quick calculations of pH using that standard value of Kw that we talked about. Question 2 is the pH of a solution where you've added 2 things together and you've ended up with OH minus in excess. It's a very simple one actually. And then the third one is to check your understanding of temperature and pH. I want you to pause the screencast so that you can just read this or screenshot the picture or something so that you can have a go at these. And in a minute, I am going to go through the answers, just the numerical answers and a little bit of discussion. I'm not going to work them all through on paper. So pause the recording now so that you can get on with these questions, and I'll see you in a minute. So I'm going to trust that you paused that and you got on with those questions all right, and you're not actually having me just tell you the answers now. So for question 1A, the answer to this would be 11.18. Question 1B, it's calcium hydroxide. You've ended up with double the concentration, so you end up with 0.001 moles of OH minus ions, and that ends up with a pH of 11. Question 2, you end up with 0.02 moles of OH minus in excess, and that leads you to a pH of 12.30. I haven't put the temperature in that. Generally, you will see that it would say at 25 degrees C, but if it doesn't tell you at 25 degrees C, but it doesn't give you a different temperature or a different Kw, then you can assume that it's at 25 degrees C. And then question 3, it gives you the pH value for water, which is 6.63. Does that mean that the water is acidic? All you need to write for this is that the concentration of H plus is equal to the concentration of OH minus. Therefore, not acidic. You can write more if you want about the pH scale only being at particular value, so therefore because it's not a 7, then you would previously thought it was acidic, but it really isn't necessary. If you look in the mark schemes, then all they say is concentration of OH minus equals concentration of H plus.